Alright, DBF team, this is video 6, I believe, of the structures series, and over the next two videos, 6 and 7, we're going to be covering arguably the hardest topic you will encounter in AA 210, which is like your typical engineering statics class here at the university. Now, what we're going to be talking about are the shear and bending moment diagrams. Today we'll do shear, and next video we'll be doing bending moment. A lot of students, myself included, I know have a lot of confusion regarding what these diagrams are, how to draw them, what they represent, and hopefully this video can help clear up some of that for all of you, while also providing an insight as to why we care about these diagrams in the first place. So all of the topics that we've talked about distributed forces, about moments, they're all going to come into play and all get summed up into a real nice, real clean shear diagram today. So to start off, we'll go ahead and draw the shear diagram so you guys can see what I'm talking about. Now in the diagram, V represents the shear force at any location along X. So it's your typical V as a function of X plot, V being the shear. So what we're going to be able to do is we're essentially going to draw a profile. It might take maybe this sort of shape, it might take a different shape, that shows what the shear force experienced at any location in our member is as a function of X. What this allows us to do is to identify the locations of the maximum shear, wherever this is at a max, and identify that as essentially a critical point. Again, in engineering, we're typically concerned with maxes, where things are going to fail. And the shear diagram gives you a very clear understanding of where those failure points might be. So today, what I want to do is run through two examples and break down exactly how we derive this shear diagram. So let's go ahead and go back to my favorite example of the cantilever beam. Let's draw a simple loading condition with a distributed load. Remember, the whole reason why we do cantilever beam modeling is because we can typically say that this is a good example of what wing loading looks like. Now, wing loading profiles, as you'll probably hear from one of our other leads, isn't typically triangular or rectangular. They can be, but typically they're going to be an elliptical distribution. But for the sake of these approximations, I'm going to show them as rectangular or triangular. And if you're working with elliptical or circular or whatever type of distributions, it's the same process. You just have to identify where your centroid is, how to calculate the area under the curve, and all of those things are relatively straightforward. The concept is crucial, however. So what we're looking at here is your typical example of a rectangular load condition on a cantilever beam. Now immediately, we can go ahead and calculate for a couple of things. The first is quite simply the reaction force at Y. Now, that's going to be very straightforward. All we have to do is take the bar or the beam distance, draw the coordinates, I always forget, all we do is we take the distance and we say, okay, this entire load can be approximated as W naught L. That X down. And therefore, for the force, the reaction force at Y, we know that that's simply going to end up being W naught L in the positive direction. Now we're at static equilibrium in the Y. Of course, there's nothing in the X, so Fx is 0. Therefore, our Rx is going to be 0 as well. And it's a rectangular load, so therefore it's applied at the middle. And if we go ahead and multiply the distributed load and treat it as a point force, we can solve for a reaction moment, and that's going to come out to be W naught L squared over 2 counterclockwise, because this will create a clockwise moment, must be opposed by a counterclockwise one. So right off the bat, we know what our reaction forces and our moments are. We've done this before, that's pretty straightforward. Now, what we need to be able to do is to say, at any point in this beam, at any point, what exactly is the shear or bending moment experienced by my beam at any point along the span. Because it's all well and fine to know what the sum at the root is. Okay, we know what it has to be resisted, we know how strong our support has to be, but how strong does our beam have to be? We don't know. How do we know this isn't going to fail somewhere here, or maybe here, or I don't know? We don't. And the way to figure that out is to graph the shear force experienced by the beam at any x, or at any point, along the member, and that's what the shear diagram is. Now, how do we do that? How do we calculate what that quote-unquote shear force, the shear force experienced by this beam at any point? How do we do that? So what's commonly taught, and what I'm going to try to explain here, is we can go ahead and cut this bar at an arbitrary point. Okay, so let's go ahead and do that. So let's take this bar and let's simplify it down to sort of a free body diagram, but not really. Okay, we're going to simplify it down to a bar that has a cut in it. We're going to basically cut this bar in half. And what we're going to do is we're going to keep all of the forces on this bar. I'm not going to include the moment because I'm only concerned with the forces. Now, the length of this bar, if I make a cut anywhere, is going to be equal to x. And I think we can agree that that's pretty straightforward. And if I cut here and that length is equal to x, then the length of the other side then must be equal to L minus x. So it's pretty straightforward. We've identified the force, we've identified how long each member is. Now we're going to account for the distributed force. Okay. So we can simply sum what that distributed force is. Remember, if we make a cut here, all we're doing is we're shortening the span of x. So instead of the full beam being represented by W naught L, we're going to represent this part here by W naught x. So whatever x is, W naught times x, is going to equal that force. And this one, therefore, must equal W naught times L minus x. Now we've accounted for the body force that acts on, or I shouldn't say body force, now we've accounted for the distributed force that acts on both parts of the beam. We've cut it in half. We've accounted for everything, but this currently is not in static equilibrium. Remember, Ry was designed to resist the entirety of the distributed force. Now, because we've made a cut, Ry is not resisting the entirety of the force. In fact, Ry is greater than W naught x unless x is equal to L. And if x is equal to L, we don't have the second part. Which means this member here is going to move upward. So in order to enforce static equilibrium, we need to add the internal forces inside the member into this sort of sketch. Now what that means is those internal forces are what the member is experiencing at that point that causes this to remain in static equilibrium. So what we do is we say, okay, there must be a shear force, V, acting on either side of that member. Now you're asking, hey, why do you draw V on the right side going up and V on the left side going down? Well, first of all, the direction is determined by intuition. I know that W naught x is going to be less than Ry, therefore in order for it to be in equilibrium, shear probably has to act down in order to supplement this force and have this force sum, we're going to do in a bit, equal to 0. But also, we know that in order for, if we were to stick this bar back together, we have to add the two shears, and if they don't cancel out, we have a force that appeared out of nowhere. Right? So internal forces on either side of the member are always equal and opposite. Hopefully that makes some sense. Because remember, if we stick these back together, those V's, those shears, are going to cancel, and we're going to have exactly what we have over here. So this now is a picture that represents basically our force balance for the entire beam at any cut. Because now x can be anything, and if x changes, L minus x will also change. That will affect the sum of our body forces, and then we can simply solve for the shear at any point in the beam by force sum. Now there's two ways to do this. The first way is you can do the force sum on your left-hand member. That works fine, but you have to know what your reaction force is. Or you can do your force sum on your right-hand member, and you don't have to know what your reaction force is. And as you're going to see, when we get to bending moment, typically you're going to choose the right-hand side member because it just makes stuff a lot easier. A lot easier. Okay? But anyway, I'll do it both ways because it doesn't matter. We can solve it either way here, and you're going to get the same result. But before we start, a couple of key observations. First of all, when x is equal to 0, the internal force has to be equal to Ry. Think about, as soon as we get to this point right here, that point is experiencing Ry. Ry is acting on it at a point. But if we're at x equals to L, it has to be equal to 0. At the very edge of the beam here, if the shear is not equal to 0, the beam is moving. Okay, because we have air over here. There's air here. There is no internal force that can be applied to resist any leftover force, let's just say, at this point, x equals to L. So your boundary conditions on the cantilever beam are always at the root, you get your reaction force. At x equals to L, the length of the beam, you have 0 for your force. So those are very important to keep in mind. So we just go ahead and we do our typical force equilibrium balance. We say, let's take the left-hand member first. The sum of the forces in y have to be equal to 0. Otherwise, it's moving. Therefore, Ry, which we already solved for, which is W naught L, Ry minus W naught X minus the shear force as a function of x have to equal 0. Because both of these are acting down, Ry is acting up. Now we solve, because this side equals to 0, we just solve for our shear force as a function of x. So Vx equals W naught L minus W naught X. Now, is it satisfied? Does this satisfy our condition? So when x equals to 0, this term disappears and we're left with W naught L, which is exactly what the reaction force is. Now, when x equals to L, we have W naught L minus W naught L equals 0. So that's how you check. That's your little sanity check. That right there, that equation satisfies our criteria. But now, let's solve it from right to left. Okay, it's much the same thing. We're going to do the same process. We're going to do a sum of the forces in y. Sum of the forces in y equal to 0. But now, my v of x is applied upwards, so that's positive. And the W naught L minus x is downward, minus W naught L minus x. Let's go this way. So here's my equation. Solve for v of x. What do you know? It's the same exact equation. I just distributed the W naught into the L minus x. We get the same thing. So it doesn't matter which side that you solve from. You're going to get the same result regardless. Yeah, so hopefully that makes some sense. We're going to do a slightly more complicated example in just a bit. But the important thing to take away here is the way we figure out what the internal shear force is on this member is we make a cut anywhere. We apply 2 equal and opposite shears on either side of the cut. It doesn't matter what the direction is. We'd simply get a negative value in it. That would say that shear acts in the opposite direction. We set 2 equal and opposite shear forces, and we either solve with the left side or the right side. Note that I didn't include any moments because moments don't create shear force. They create a bending moment, a bending torque, which is fundamentally different. So that's why I didn't include moments. You only have to take account for your forces when you're dealing with shear. So hopefully this made some sense. We'll go ahead and we'll actually draw the diagram here. I'll erase this and draw the diagram above it real fast so you guys can see what this distribution looks like. Now typically you're going to see in classes they're going to say that shear force is positive downward. It doesn't really matter. You can draw it either way you want. But anyway, so if you get a positive shear, it's just going to be on this side of the axis. It's kind of weird, but hopefully it makes some sense when we look at bending moment. But for now, just shear is positive downward. So what do we have? We have W naught L at the wall. So when x is equal to 0, we're at W naught L. When x is equal to L, we're at 0. At L. Now what's our curve look like? Well, we have a rectangular distribution, and that causes a linear curve. As you can see, W naught x is linear. And it's going to decrease by a set amount all the way to W naught, or all the way out to x equals to L. So our shear diagram simply looks like that. And what's that tell you is that the max shear is experienced at the wall, which is typical for cantilever beams, unless you're under some weird loading condition. So there you go. There's your shear diagram there's your shear force as a function of x for the simple distributed load criteria.